Okay, welcome to CS 473. This is also called 498 DL1, and eventually it will be called 473. So this is basically a mixed undergrad and grad level algorithms course, and some of you who have been here for a while may be aware of some of the curriculum changes we made, and but don't worry, it's you don't need to know all the history of how this course came to be. So there will be two instructors. I'm Chandra Chekuri. I've been here for 10 years. I do research in algorithms primarily, and there's Ruta Mehta. She works in algorithm game theory and related topics, and she just joined us this past spring. So part of this course is also for her to get used to this course and then be able to teach later on her own. So let's see. I will go through basically quickly some administrative stuff that you should know about, and then we'll go through the lecture on fast Fourier transform. Okay, so let's get through this. So we have two TAs, Shalmali Gupta and Patrick Lin, both graduate students in algorithms, and you'll find information on how to contact them, etc., on the web page. In general, there's a lot of useful. Most of the information is on the web page. I don't want to repeat all that here, so I'll only highlight a few things. You need to sign up for Piazza and use it primarily if you want to reach us, unless it's really something private related to your health or something that you don't feel comfortable using Piazza for. So things like, I forgot to submit the homework, right? Don't send us email because there's a lot of you. So just use a private note on Piazza so that we can also track it. Somebody says, I want a conflict exam, and then if you send email, and we may forget who said what. So it's better to use private notes on Piazza for us to keep track of information such as those requests and so on. We'll have office hours. All that stuff is on the web page. That's a link to the web page in case Google doesn't help you. So grading, we are going to do an experiment this semester. You will be submitting your homework as a PDF on this site called Gradescope, which is sort of a new grading system that UC Berkeley people developed. It's supposed to make grading a little easier and more consistent in terms of being close to the rubric and provide flexibility. So we're going to try this out. And Gradescope is kind of, I guess, still a little bit in development, so there may be a few issues here and there. One of the things that is not completely clear to us yet is whether it's FERPA compliant in terms of keeping information confidential and stuff. So there is a little bit of ambiguity. And for this reason, we are asking you to create an alias if you want to. Right, it's up to you. Right, if you are uncomfortable putting your university net ID and actual proper name on Gradescope, make up something. Right, create a new email address on Google or wherever else, and tell us the mapping. Right, you say I am so and so. Right, so that we can map your Gradescope alias to your actual net ID, so that we can keep track of the grades. Okay. So Patrick has already set up something in Moodle, which is run by the university, where we ask you to give us the email address that you used on Gradescope. So you don't have to use your university email address if you're uncomfortable. Okay, you can make up something, right? So that's where you'll be submitting homeworks, and that's also where you'll be submitting regrade requests and things like that. But we'll actually maintain the grades on the university system on Moodle, right, so that we don't release that information, and you should use Piazza for announcements, questions, discussions, and things like that. Okay, prereqs. As I said, this is not a first level algorithms course. but we understand that not everyone will have a uniform background, and you have to judge a little bit whether you have the right background or not. So if you are familiar with the courses at UIUC, we want you to have 173, 225, and 374. Okay, not all of you would have taken 374. Some of you, or many of you, are grad students and stuff. But I put down a concrete list of things that we would assume. We won't cover those, and if you're not comfortable with that and you're good enough to catch up, that's fine, right? But we can't revisit those in lecture, right? So I mean, some of the things is that you should be able to write a proof, right? And this is a class about writing proofs about algorithms, design, and writing proofs of correctness. So if you can't write proofs, it's going to be tough, right? You need to have some exposure and ability to think in recursively. We're not going to explain recursion. You should have some basic data structures at least, right? This course is not going to be heavy on data structures at all, but still we will use basic data structures. You should have good comfort with basic graph algorithms, right? You know, reachability, DFS, BFS, and undirected versus directed, strong connected components, and shortest paths, right? Not negative lengths, but the basic Dijkstra's algorithm and minimum spanning trees and so on. And we will, a portion of the class is on randomized algorithms. So you should have comfort with basic discrete probability. You should know what expectation is, what variance is, and so on. And finally, you know, we'll discuss towards the end NP completeness and intractability and stuff. But if you've not seen it, it's okay. But having some notion of what does it mean to have a model of computation, and what is NP if you had heard of it, or what is undecidability would kind of help you, but it's not really required. Okay, there's some, we are going to provide, we have pretty good notes for all the things that we cover. We'll provide pointers. There's some good books. There's a nice book by Dasgupta, Papadimitriou, and Vazirani. You can find a PDF. They used to keep it online for free, and then they stopped, but you can find copies. I linked to one. And there's also a nice book by Kleinberg and Tardosh. And there's good notes by Jeff, Sariel, and some slides that we'll provide. So there's no lack of material, and we expect that you'll actually read on your own quite a bit. Okay, so quick overview of the grading policy. There'll be 2 midterms, and basically 10 homeworks, basically including homework 0, 11 homeworks, basically every week, with some gaps for exams and stuff. And that's the percentage of the that's the credit for the homeworks and midterms. That's the distribution. And we already figured out the dates for the midterms. You should put that in your calendar and not come on the last day and said I forgot, right? So the final exam is also tentatively decided, partly because this is a scheduled section, and so it will be the first day of exam, so keep those in mind. Homeworks, a lot of information is on the website, but basic idea is 1 homework every week, 2 to 3 problems, mostly 3 problems, and you can work in groups of up to 3, except homework 0, okay? And pay close attention to academic integrity policies. Make sure you read it properly. Don't complain later saying that you didn't tell me, right? It's part of your job to read the policies of the course, okay? We're not going to have extensions or homeworks unless you really have a big health reason, you fall sick and stuff like that, saying that, I was driving home and I couldn't get here on time. We don't want to deal with that. So in order to give you some flexibility, we are going to drop basically 5 problems from the homework, right? The lowest 5 problems, right? So you get to choose how you want to use it. Maybe you say, okay, this week I don't want to do any homework. That's fine, right? And so it roughly 2 homeworks will drop, okay? So read the instructions on the website. Okay, you are not, most of you have taken a lot of courses, but still this is a bit intense course for people who are not maybe naturally theoreticians, right? So don't delay things, don't delay studying, don't try to have your partition the work and have your friends do the work for you, because then you will get into trouble in the exams, okay? So take that, that's the main message I want to give you. You can look at it later. Homework 0 is on the class website. It's due next Tuesday at 8 p.m. It's mainly to get you to understand the level at which this class will be and to give you some background on what we expect you to know. And this is something that you need to do on your own and submit separately. I updated the homework late last night after it was already there, so I changed something. So in case you downloaded it earlier in the day yesterday, download it again, okay? Okay. If you have any special needs and you need some accommodations, contact the instructors privately. Okay, you can send us email for these kinds of things. Some of them have dress accommodations and stuff for exams. Let us know. Lectures are being taped in case you miss class, but don't try to use that as an excuse to sit at home. I think it's hard to watch videos, right? At least for me, right? So I think it's good to come to class. So this is just, I got a message from the police saying, put this emergency information on the, right? Just in case, right? You know how to escape this room, right? Look at the exits and stuff, right? It's like going on a plane, right? Okay. So a brief overview of what the course is about, right? And basically the course is divided into 4 parts. The first few weeks is on recursion and dynamic programming. Okay? Just to bring you back, now some of you have seen dynamic programming. We'll do a little bit more advanced topics, maybe advanced examples, give you some perspective which is more advanced than a basic undergraduate algorithms course. The second part is going to be on randomization in algorithms and data structures, and that's a very powerful paradigm that has emerged over the last several decades, but it's used all over. So we'll give you some introduction to randomization in algorithms. And the third part is on combinatorial and discrete optimization. We'll start with network flows and matchings, and then do linear programming and maybe touch upon convex programming to give you a sense of where these things fit in the bigger picture, and connections to basically integer programming and discrete optimization. So that's a big chunk of the course, and then we'll close with discussion of NP completeness, intractability in general, and how do you address intractability by using approximation algorithms and heuristics, and how do you think about them, okay? And yeah, those are the 4 big pieces of the course, okay? What else? The main goals, I guess, are to teach you and expose you to certain basically fundamental problems in algorithms. Like, for example, we'll start today with fast Fourier transform, hashing, universal hashing, flows and cuts, matchings, linear programming. These are not any problems, right? These are fundamental results and problems that is just good to know, right? And they're tools that you can use to solve other problems. So that's one goal of the course. The other goal is to expose you to design principles like using randomization or recursion and dynamic programming, or using optimization. What are the tools in optimization like convexity and duality, and what are tools in how do you think about approximation and heuristics. And then I think also what's important is to expose you at the second level of algorithms that algorithms are tricky to design. It's not easy to figure out what is the best algorithm for a given problem, right? And one of the things that we hope that you will realize is the power of mathematics in algorithm design, right? And in particular, you will see tools from geometry and algebra and probability, convexity, playing an important role in figuring out good algorithms for seemingly unrelated problems, right? So the more mathematics you know, the more tools you'll have Okay, so that's also something that the exposure to those things will be a theme in the class. Okay, so most of the class is basically about algorithm design, right? But it's good to we'll come towards intractability and hardness and some of those things towards the end of the class. Sometimes this topic is done at the beginning of the class, but for whatever reason, we at least I decided that maybe we should do it at the end. But it's good to have this terminology in place, which I assume most of you are familiar with. But just to be on the same page, we are interested in broadly, we're not interested always in one particular problem that may not be of so much interest, right? We also want to think about collections of problems and how do we think about them together, right? And what does it mean for that we have an efficient algorithm for some problem or we don't have something, right? So to make sense of that, we think of broad complexity classes of problems, and we say that P is a set of all problems which have efficient algorithms, where efficiency is crudely classified as having a polynomial time algorithm. Okay? So that's called the class P. And then class X is this class of problems which have exponential time algorithms. For many problems that you will see, it's easy to come up with a brute force exponential time algorithm. Not all, but many simple problems that you see, it's easy to come up with a brute force solution which will solve the problem in exponential time. So X is an interesting class because many problems that we can encounter can be solved in exponential time. But there's an intermediate class called NP, which is called non-deterministic polynomial time, and that captures many problems that we want to solve. And it's easy to prove that NP is in exponential time, that every problem in NP has an exponential time algorithm. But we don't know whether NP is equal to P or not. And so that's a big open problem, right? And it has many interesting concrete and philosophical implications. So that is perhaps the most important open problem in theoretical computer science. And why is it interesting? We know that P is a strict subset of X. That means there are problems in exponential time which cannot be solved in polynomial time. We don't know the same for NP. So we know that P is a subset of NP, is a subset of X, and P and X are different, right? So where is NP? That's an interesting question. And then, of course, we take it for granted that problems have algorithms, because if you don't care about efficiency, we can always solve a problem. But that's not the case, right? There are many problems for which, very interesting problems, very simple problems even, for which there is no algorithm, right? They're called undecidable, right? And if you actually walk across to people who work in programming languages and formal methods, they mostly work with problems of that kind, which are undecidable, right? So they're working at a different scale. They're not working at the level of P and X or something. They're working at the level of, is this even problem even decidable, right? And it's not like they're made up problems. They're important problems, okay? So for the most part, we will not be dealing with that level of hierarchy, right? Where we're worried about, is there even an algorithm, right? But we'll be at a lower level, but it's good to know that there are undecidable problems and stuff. So that's just maybe in the lecture, or I'll say it's NP hard. Okay, if you don't know what NP hard means, it's okay, right? But just assume that it's a hard problem as far as we know, right? Or if in the homework I'll say, okay, we don't know how to solve this problem. So just to give you a context that it's a hard problem, right? So even though I'm not formally defining that till we come later, it's just good to have that terminology. Okay. All right. So there are some, I'm not going to go through this. You should go through this in the sense of later on in terms of thinking formally about algorithm design. There are some sort of a checklist that it's good to go through, right? Whenever you find a problem is hard, you should think about, what's the input, what's the output, what's the model of computation, try to use existing problems, try to use existing paradigms. As you find maybe non-trivial problems that you're trying to solve, use some kind of a checklist to kind of walk through what is it that you may be missing, okay? So I won't go through that, that's just a sort of a checklist for you. So any questions so far on the administrative details or the course goals? Maybe, as they say on airplanes, right? If this is not the destination you want to go to, right? Time to step off the plane, right? So I just in case this is not the right course for you, there's plenty of time to step off. Okay, so let's go to a very interesting algorithm and problem that we'll start with. It's called the fast Fourier transform. Any questions so far? Everybody okay? Right? Okay. Okay. So this is the rest of, today and on Friday we'll cover this what's called the fast Fourier transform and also called the discrete Fourier transform. Just to advertise it, right? It's a extremely useful algorithm in practice, right? It's a fundamental algorithm in practice. IEEE calls it one of the top 10 algorithms of the 20th century, right? It's surprisingly that very few people actually teach it in basic algorithms, even though it's part of the reason is that it has some numerical issues which are hard to explain in lecture. So we won't go over that, but the goal of this is to expose you to the problem, the applications a little bit, and the simple divide and conquer methodology that underlies FFT. It's a very simple algorithm in retrospect, right? But it involves some mathematics, which is also nice to see, and hopefully we'll see more examples of that, and you can build on this as we go along. So that's the goal of this FFT, understanding FFT, and it's also very surprising, and so we'll see parts of it. Okay, so let's start. Everybody knows, I assume, that what a polynomial is, right? In one variable, right? You have a variable x, and a polynomial is simply basically linear combination of monomials of the form x, x to the 0, x to the 1, x square, x cube, and so on, right? It's it's a simple class of functions, but they're a very powerful class of functions, right? Because there are some fundamental theorems about how polynomials can represent any function to arbitrary desired accuracy, and they come up in many applications, right? So given a polynomial, the degree of the polynomial is the highest coefficient, which is non-zero, right? Highest power of x with a non-zero coefficient, right? That's the degree of the polynomial. And how do we think about, here is an example, p of x is 3 minus 4x plus 5x cube, and degree is 3, and we have some coefficients which are 0, like coefficient of x square is 0 in this one, okay? So, okay, how do we think of representing a polynomial, right? If I say, okay, give you a polynomial, how do you think of representing it? Normally, when we think of a polynomial, we just think of it as basically a coefficient representation, right? We have the degree and coefficients a0, d, where d is the degree, and just for simplicity, because we want to think of n as the size of the input, we'll assume the degree is n minus 1, right? It's just a shift, right? So the natural representation of a polynomial is the coefficient representation, right? Okay, so there are some basic things that you would like to do with polynomials, right? What are the most basic things you can think of when we think of doing things with polynomials? Okay, if I give you a polynomial, and a number, evaluate the polynomial at that number, right? It's a function, right, of one variable, so give me the value of the polynomial. Or you can want to add two polynomials, right? Or you want to multiply two polynomials. And polynomials, root finding of polynomials is also a very important thing. Polynomial root finding comes up in many applications. Okay, so let's see algorithmically how fast can we do these operations, right? If I give you a polynomial and say, evaluate it at a number, what do? You just plug in that number, right? So what does it mean, right? Well, it is a very simple algorithm, right? You just evaluate You just add up compute all the terms and add them up, right? Okay, now how do you compute all the powers of alpha up to the degree? Well, you can keep a running counter, right? You compute the power, you increase the power, you multiply with alpha each time so that you keep a track of the alpha to the I as the I goes from 0 to the degree, and just add them up with multiplying with the coefficient. Right? Nothing complicated here. Yeah? Okay? All right. So, if you just look at how many multiplications did we do and how many additions did we do, we'll do n additions and basically 2n multiplications. It doesn't matter, O of n. Okay. You can do a little better. If you're a little bit careful, Horner's rule can be used to cut the multiplications in half. So, okay, it looks like we can do this in linear time, right? Nothing complicated about this, right? Okay, so the only thing you have to be a little careful is that numerical issues, okay? All right? If I give you, say, even a simple polynomial of, say, of the form x to the n, and I ask you evaluate the x to the n at 2, right? The polynomial is just x to the n, and then I say, evaluate it at 2. What is the size of the output, right? What is the answer, right? It's 2 to the n, right? Okay, it's much bigger than your input, yeah? Okay. So if you actually, naively implement this algorithm and you don't pay attention to numbers, it will blow up on you. Okay. So polynomials, even though they look simple because of the power exponentiation, you can start with a simple number and get a big number, right? So you can run into precision issues and stuff, but we'll ignore that because in practice, polynomial evaluation is not done naively like this. In practice, polynomial evaluation is done in a field where you you do it on a finite field so that you don't let the numbers grow very big. Okay, let's not worry about that. I'm just saying that it's always important when you deal with numerical algorithms at the back of the mind to worry a little bit about numerical issues, right? And FFT is a little bit complicated because of these numerical issues, but we'll ignore it for the most part and focus on the discrete aspects because it's too far beyond the scope of this class to deal with this. Okay. So let's go back to the simpler issues. If I give you two polynomials and say add them up, how will you do it, right? It's very simple, right? You just add up the coefficients, right? So implicitly we are saying, I'll give you two polynomials in a particular representation, and I'm saying, give me the representation of the polynomial that is the sum of these two polynomials. And in the coefficient representation, it's very easy, right? We just add them up, okay? So that's linear time, so nothing fancy about that, right? You just add up. If they are a little bit degrees or a little bit different, we just pad with zeros and you just do. Okay, good. Okay, what about multiplication? Right? If I give you two polynomials and say multiply them, well, we know how to multiply them too, right? The only question is complexity, right? How do you multiply two polynomials? Right? So you say, okay, the way we multiply polynomials is, we say think of this as we have, say 5 plus 3x plus 10x cube times 1 plus 3x square. How do we multiply? We basically multiply term by term, right? We say, okay, we multiply 5 times 1 plus 3x square, you'll get one polynomial, that's easy to do. And we multiply 3x times the polynomial, right? And we get another polynomial, right? And then we multiply 10x cubed, right? The obvious thing. And then we add them up, right? Another way of looking at it is, look at look at the output and look at x to the I and say, what is the coefficient of x to the I if I multiply these two? Then that is the formula for that, right? You look at all ways of getting x to the I by multiplying these two polynomials, right? And no magic here, right? The only question is how long does it take? This is the standard way we multiply numbers also, right? If you multiply two numbers, this is how we multiply, right? Digit by digit, right? And then we add up all those things. If I give you two n degree polynomials, what's the running time of this algorithm? It takes n square time, right? Yeah? Even if you use the formula, it takes n square time, right? Why? Because basically, we are doing n time to multiply a term. You get one polynomial, and we get n polynomials, and we have to add all of them up. Yeah? So this seems like this is the definition of multiplication of two polynomials, right? So the question is, can we do it faster than n squared, right? And surprisingly, you can, right? What we'll see is that you can actually multiply two polynomials in n log n time as opposed to n squared time. Okay? And that is the fast Fourier transform based algorithm, right? So so now why is this multiplication of two polynomials? You may think the multiplication of polynomials, I never see polynomials most of the time in my life, so why do you care about multiplying two polynomials? But there are many reasons why people care about multiplying two polynomials together, and because that basic operation of taking two vector representations of the coefficients of polynomials and looking at the coefficients of the product is called the convolution of these two vectors. Okay, so that has independent interest and many applications. So given two vectors a0 up to an and b0 up to bm, the vector c0 up to cm plus n, which is defined by that formula, which is simply the coefficient of the product of those two polynomials, is called the convolution of those two vectors. Okay, it's some kind of strange product, right? It looks like it's a definition between two vectors, right? So it's called the convolution of those two things, right? So it is basically the same as multiplying two polynomials and looking at the coefficient representation. Okay, so we want to compute the convolution of two vectors in a fast way without doing it in the obvious way. Okay, and can we do it? And it turns out that you can, and that's why it's a very, very interesting thing, algorithmically and as application wise. Okay, so now let's try to figure out how can we do it faster, right? It seems like difficult to imagine that one can do it faster given that this is how we think of the definition of the problem, right? That's the thing about algorithms, right? The definition is not necessarily the way one should necessarily compute it, right? There may be alternate ways of computing which can be very clever. That's why designing algorithms is hard, and we learn how to do these things. So the first key step in trying to figure out how to multiply these two things faster than the obvious way is to basically say this is a key idea, this is not obvious, is to think about changing the representation of the polynomial. Okay, so we think of polynomial as being given in coefficient form, right? And if you want to multiply that in the coefficient form, we sort of didn't seem to have much leverage because the definition is what we're stuck with. Okay, but we'll see that it's useful to think about multiplying polynomials by thinking, can I think of representing the polynomial in a different way? Okay, what are different ways of representing polynomials? One of the first things we learn in basic quadratic polynomials and stuff is, we can compute the roots of polynomials, and we learn the fundamental theorem of algebra eventually that over the complex numbers, every polynomial has a unique representation as factorization into roots. Okay, and so we can say, okay, look, I can represent a polynomial in a different way by giving you the roots of the polynomial, right? Yeah, and that's a unique representation, right? Every polynomial can be represented by the roots, assuming that we factor out so we take out the coefficient of that leading coefficient is we normalize it to 1, and then we can represent it as the root representation. Yeah, does it make sense? Okay, so I can say instead of giving you the coefficient representation, I'll give you the root representation. So let's see, suppose instead of working with the coefficient representation of polynomials, we work with the root representation of polynomials. Okay, does it buy us something, right? And in fact, it is not hard to, let's go back and figure out all the basic operations we want to do. Let's see if the root representation helps us. Okay, and in fact it does, right? If you want to evaluate a polynomial using the root representation, it's very easy, right? Yeah, so my polynomial is x minus r1 times x minus r2 times x minus rn minus 1 with some leading coefficient. and I want to evaluate that polynomial at some number alpha. What is it? It's just alpha minus r1 times alpha minus r2 times all the way to alpha minus rn minus 1, and so it's just multiplying n additions and n multiplications, the same thing as we had a quotient representation, right? It's not any more complicated. What about multiplication? Multiplication becomes very easy if you have a root representation, right? It's completely trivial. What is the multiplication of two polynomials if I give you the roots of the polynomial? It's just all the roots combined of this polynomial and that polynomial are the roots of the product, right? So I don't have to do anything, I just have to list for you all the roots, right? So multiplication becomes trivial if I gave you the root representation. What about addition though? Addition is complicated, right? Okay, if I want to add two polynomials in the root representation, that's very difficult. We have to first expand it out and then add them and then go back and find roots of that. It's even worse. Finding roots is very hard, right? Because they could be rational and complex, and right. But multiplication was trivial. So see, this is a key idea, right? Changing the representation makes certain operations much easier than other operations, right? Okay. Okay. So roots are also not very good. Root representation is a pain, right? Because polynomials have, we can't even give a finite representation of a polynomial in the root thing if they have irrational roots and stuff, right? And that's a pain. So normally that's not a good way of representing polynomials. So here is another representation of polynomials which turns out to have nice properties, and that's to represent polynomials not by roots or by coefficients, but by representing polynomials by evaluating them at specific points. Okay, so root is, you can think of the roots of a polynomial those are the points where the polynomial vanishes, right, becomes 0. Okay, it turns out that you don't have to use the roots. Let's do the following representation of a polynomial. I pick some, say the degree of the polynomial is n minus 1, and I pick basically n points, n values, x0, x1 up to xn minus 1, distinct values, and I evaluate the polynomial at x0 up to xn minus 1 and let the values be y0 and yn minus 1. Okay, so I just store x0, y0, x1, y1, xn minus 1, yn minus 1. What am I saying? You know, this is the value of the polynomial at each of these distinct samples. Okay, for any function you can do that, right? You can take any function and say what is the value of this function at this point, this point, this point, this point, right? But what happens if I give you a function and say, look, you know, if you evaluate it at this thing, it is this value, and so on, and a few of these things, can you reconstruct the function from that information? In general, you cannot, right? There could be huge number of functions that can go through the same points, right? Maybe many complicated functions can have the same values at the same points, but different values at different points. There is no uniqueness, right? However, polynomials are special because of the fundamental theorem of algebra that if I give you a degree n minus 1 polynomial, evaluating it at n points is enough. Okay? So you can check that there is a unique polynomial. I mean, we'll see this, a sketch of the proof. We want to claim that if I give you n evaluations, there is a unique degree n minus 1 polynomial which goes through those points. Okay? Okay? So let's see one part of that, right? So here is what I'm claiming, right? So I'm trying to argue that the sample representation is a valid representation of polynomials. Okay? So okay, here is so that's what we'll ignore that issue for now. Let's see. Okay. So the claim is that if I give you n tuples x0, y0, x1, y1, xn minus 1, yn minus 1, there is exactly one polynomial which goes through those points, which has those right values, where x0, x1 are distinct, right? I have to make them distinct. x0, x1, xn minus 1 are distinct. Okay? Is the theorem statement make sense? It's exactly one. Okay. So let's argue that there is at least one polynomial which goes through these points. Okay, if there is exactly one polynomial, I have to show you that polynomial and then argue that there cannot be two polynomials which are different but share the same values, right? Okay, so representation is valid. Okay, so here is a reason why there is a polynomial which goes through all those points, and it's called Lagrange interpolation. Okay, it's a very well-known and simple idea. So if I want to tell you that there is a polynomial of degree n minus 1 which goes through exactly those numbers, right, x0, y0, x1, yn, here is how you create it. It's easier to see with n equal to 3. Remember, I give you how many numbers? Three tuples, right? x0, y0, x1, y1, x2, y2. Here is a polynomial which has the property that at x0 the polynomial has value y0, at x1 the polynomial has value y1, and at x2 the value has y2. How do we create that? You know, it is y0 times x minus x1 times x minus x2 divided by x0 minus x1 times x0 minus x2. What's the interesting thing about that? If you plug in x equal to x1, what happens? At x1 or x2, that if I put p of if I put x0 into that, what happens to that term? This let me see. I don't have a, okay, you can see this, right? You can easily see that if I plug in x0 into this polynomial, you'll get y0, right? Why? Because those two terms will disappear, right? Similarly, if I plug in x1 into the polynomial, you'll get y1, right? And if I plug in x2, I'll get y2, right? And you can see that it's a polynomial, right? Yeah, and its degree is basically n minus 1. Okay? So given these numbers, tuples n numbers, I can create a degree n minus 1 polynomial which has a property that the polynomial actually goes through those numbers, right? Yeah? So what did we prove? We proved that there exists a degree n minus 1 polynomial which exactly goes through those points. Now, we had also argued that there cannot be two polynomials which go through that. Okay? Maybe there are two different polynomials which go through these points. Okay? And then the representation is not valid, right? There is no uniqueness. Okay? Is that point clear? Okay? Ask questions if this is not clear, right? It is a good place to pause, right? I'm saying that if I give you n numbers, n tuples, x0, y0, x1, y1, xn minus 1, yn minus 1, okay? Then there's only one polynomial, and where the assumption is that x0, x1, xn minus 1 are all distinct. They cannot be the same, right? No two of them can be same. Then there's exactly one polynomial which has the property that p of x0 is y0, p of x1 is y1, p of x2 is y2, and p of xn minus 1 is yn minus 1, and its degree is n minus 1. It is exactly one degree n minus 1 polynomial. Yeah?
Is this Lagrange interpolation the only way to reconstruct
This is the most general way of reconstructing, right? You know, in the sense that we are proving that there exists one polynomial, right? There could be other ways of, for a particular set of values, there will be other ways of doing it. But this is the general way of doing it, right? It's not the only way, yeah. Yeah. Yeah, degree will be at most n minus 1, yeah. And actually, no, you cannot have, if the numbers are distinct, you cannot have less than n minus 1. Yeah, you need n minus 1 degree. Because it's a valid representation, you need n minus 1 degree.
Like if the 3 points are collinear, then the polynomial that will satisfy would be linear polynomial.
If the I mean, yeah, I mean, in the sense that, you know, yeah, if you have n minus 1 degree with the guy as 0, yes, that's yeah, it's okay. No, so there's one-to-one correspondence between the coefficient vectors and these points, yeah. Okay. Okay. Now for the second part, we just saw that if I give you this tuple, there is one polynomial which goes through it, right? Now we have to argue that there are, you cannot have p of x satisfying this and p prime of x satisfying this, such that p of x is not equal to p prime of x. Okay? Now for this you can use the fundamental theorem of algebra to prove it. Okay? Alright? So that if you have two different polynomials, then you will get a contradiction with fundamental theorem of algebra, because you'll have p minus q, right? P and q are distinct and they agree on all n points, right? Then argue that, you know, that the uniqueness of the roots will be violated. Okay? Okay, this, think about this, and if you have questions, we'll discuss it later. Okay? So there is exactly one polynomial which goes through these n points, and so it's a valid representation. What does it mean? It's a valid representation. Let's stress it again, that if I give you a coefficient representation a0 up to an minus 1, then you can map it to a sample representation, and there is a unique correspondence between that, right? You know, you can't have two different polynomials mapping to the same sample representation. Okay? So that's what it means to be a valid representation. Okay? Okay. So now let's see, you know, suppose, you know, instead of using root representation, we give the sample representation. Does it help us do these operations in an efficient way? Right? Okay, and let's go back to this. So what is the sample representation? I'm going to give you n tuples, you know, x0, y0, x1, y1. That is what I'm saying is that, you know, at x0 the polynomial is at value is y0, at x1 it is y1, and so on and so forth. Now there are two different polynomials, right? And I say, you know, add them up. Or okay, so let's go through the how will we add two polynomials in this representation? So I need to tell you what is the value of the polynomial at sum of the polynomials at x0. Well, it is the sum at, we have both the values at x0, right? y0 and y0 prime, right? For the two different polynomials, we add it up, right? If I tell you the value of the polynomial at a polynomial p, I mean using a at x0 and b at x0, what is the value of the polynomial a plus b at x0? It is a of x0 plus b of x0, right? Which is y0 plus y0 prime, right? We just add them up, right? Is that clear? Yes? Addition is easy? Yeah? Yeah?
What if the x values are different?
No, we need the same x values. Right? You know, remember when I say sample representation, we need the same x0, x1, x1 for all the polynomials. Otherwise we can't add them up, right? Yeah? Yeah, the polynomial should be of the same degree. Yeah, otherwise we are in trouble, right? So we'll work with the same degree, basically. Yeah, that's a good point. Yeah. Okay. Now the thing is, multiplication is also easy, right? Why is that? Yeah, I mean, if I know the value of the polynomial at x0 and another polynomial at x0, and I want to multiply the thing and want to know the value at x0, we just multiply the numbers, right? Okay. So multiplication is also easy. There's a little bit of a catch, right? We are a little careful, because when you take the product of two polynomials, the degree increases, right? So we won't get a valid sample representation unless we pad the original polynomials and get its representation with the higher degree. Okay? Does it make sense? Because the degree increases of the product of the polynomials, right? So if you want to get a valid sample representation, we need to start with the initial polynomials with some padding. Otherwise, we won't get the right degree bound. Okay? We'll worry about it a little later. Okay? Okay, but the multiplication is also easy, right? So this seems to be the best of both worlds, right? We are doing addition very easily and multiplication very easily. Okay? So that's nice, right? Okay. So also we realize that there isn't much complication with irrational numbers and stuff like that, right? If I choose x0, x2 up to xn minus 1 as simple numbers, my y0, y1, yn minus 1 also will not be irrational or anything, right? So they'll be fine too, right? So we don't have these numerical issues, at least the ones we face with roots. So the sample representation seems to give us the best of all worlds, right? Addition is easy, multiplication is easy, and evaluation is also easy. Evaluation is not so easy actually, right? Evaluation is tricky, right? Okay, so how will you evaluate at a different point, right? Evaluation became hard now, right? If I only gave you the value of the polynomial at some particular points and say, give me a value at a different point, how will you evaluate it? Lagrangian interpolation, good, right? Because we know what is a polynomial actually, right? By Lagrangian interpolation, we can construct the Lagrangian interpolation. Okay, but then how long will it take? How big is the Lagrangian interpolation? It's big. Okay, it takes n square time to evaluate now. Okay, right? Evaluation became complicated, which seems the easiest of things, right? Okay, so see, the representation has made it easy for us to multiply and add, but evaluation is hard. Okay, so but let's go back. See, really, what we want to do is multiply the polynomials in the coefficient form efficiently, right? What we are realizing is, if you had the sample representation, somehow multiplication and addition are easy, but we don't have it. We don't have it in the coefficient form. So the idea is that can we go from the coefficient form of a polynomial to the sample representation of the polynomial? If you can do that efficiently and you can also go back efficiently, what can we do? We can start with the polynomials in the coefficient form, convert them into the sample representation, do the multiplication, because it's very easy there, and go back. Yeah? So it will work only if the process of going from the coefficient representation to the sample representation is somehow easy. Okay? Or that is efficient, then we have a nice way of going from multiplying to polynomials fast. Does that make sense? Okay. So the second key idea is, can we go from the coefficient form to the sample representation easily? Okay. Now, why should we think that it is possible to do? Well, it is not easy, right? If I give you, how do I pick this x0, x1 up to xn minus 1, right? I give you the coefficient polynomial as a coefficient form, a0 up to an minus 1 is the coefficients of the polynomial, and then I'm asking you to create a sample representation. What is the sample representation? You have to pick some numbers x0 up to xn minus 1 and then evaluate the polynomial at those numbers, right? But we saw that evaluation for at any particular number takes n time, so if I want to evaluate it at n numbers, it takes n square time, right? So the only idea, the main idea, which is the idea is that you get to choose x0 up to xn minus 1. I don't get to decide. You have the freedom to choose x0 up to xn minus 1 carefully, so that you don't have to evaluate them in the naive way of saying, I will evaluate the polynomial at x0, forget about all the values, then I'll go to x1 and evaluate the polynomial again, then I'll take x2, evaluate the polynomial, right? If I choose the numbers that I evaluate the polynomial at carefully, can I find the value of the polynomial at all these numbers faster than evaluating them separately? That is the second key idea. Okay? Remember, the sample representation is up to you which numbers you choose, x0 up to xn minus 1, as long as they are not the same. Right? You get to choose where you want to evaluate the polynomial. Okay? Can we figure out nice numbers to evaluate at, so that we can reuse the work that we are doing to evaluate one number in the other number? Okay, that is the second key idea. Okay? Is that clear? Okay, that's a flexibility you have. You get to choose x0 up to xn minus 1, and let's see if you can choose them carefully. Okay? Okay, so how do we do that? So how do we do this to save work? Let's take the we'll do some simple observation, right? For simplicity, we'll assume that n is a power of 2, right? N is a power of 2. That's just to make some recursion easy. Okay, it's not a big loss, right? Assuming that n is a power of 2 is not a big loss, right? Why? If the polynomial is of degree 10, why should I be okay if I assume it's the power of 2? Right? Yeah.
You can add degrees with zero powers.
Yeah, you can add, right? And we're not increasing it too much, right? Every number is between 2 powers of 2, right? And which are not too far apart, so it's okay, right? Okay, it is a very simple observation, right? If I take, suppose I give you this polynomial, right? 3 plus 4x plus 6x square plus something like this, right? We can break it up into even powers and odd powers, right? Yeah? Okay. Now, what is the advantage of breaking it up into even powers and odd powers like this? Well, we look at the odd powers, we can take x out of the odd power, right? So, what do we get? We get the original polynomial is the sum of the even powers here, and then if you factor x out, we get another polynomial which also has even powers. Yeah? Okay, seems like an obvious thing. What is the benefit of that, right? Well, so here is the point, right? Suppose somehow I calculated the value of the polynomial at some number x. I already gave the, right, then I claim that somehow you should, it's also easy to compute the value of the number minus x. Okay, so actually this is not quite true. Suppose I told you that I calculated this value for at some x and this value at some x as well. Then I claim that if I want to calculate the value of the polynomial at minus x, I can figure it out, right? Because the value here is the same, the value here is the same, except that when I combine this, I have to multiply it with the minus x here, right? So if I actually gave you the polynomial evaluation at x, then evaluating at minus x is easy, right? Okay, can we exploit this, right? And to explore this idea, let's formalize this. Suppose I give you a polynomial a of degree n minus 1, and where n is the power of 2, we'll break it up into two polynomials, odd and even, a odd and a even, where a odd is all the odd powers of the polynomial, and a even is all the even powers of the polynomial. Okay? And then what can we do? We can write the polynomial a of x as a even of x square plus x times a odd of x square. Yeah? Make sense? Yeah? We broke up the polynomial into just two smaller polynomials of half the quotients. Yeah? Is it clear what we did? Okay. Okay, so now basically, suppose we did the following, right? Remember, we get to choose the samples, right? Right? We control. So let's choose them a little bit cleverly, right? For the high level, right? Instead of choosing x0, x1, x2, xn minus 1 all independently, let's choose x0 up to xn over 2 minus 1. And minus x0 minus x1 up to minus xn minus 1 up to minus 1. These are the same numbers with the negation of the sign, right? Instead of choosing n numbers which are all completely arbitrary, we picked first n over 2 arbitrarily, and the next n over 2 numbers are actually negations of the first n over 2. That's fine, right? They are distinct numbers, right? Okay. What's the advantage of this? So okay, so the only reason that is useful is that if I compute the odd and even polynomials at the first n over 2 numbers, I don't have to compute them again at the second n over 2 numbers. Or I need to do some computation, but it's very easy, right? Because the square of those numbers is the square of the previous numbers. I still have to do a little bit work of putting them together. But that's easy, right? So I saved half of my work, right? Yeah? I didn't have to. Okay. Now, if we can make this work recursively, we will get basically a very efficient algorithm. Okay? Alright? So that's the goal. Okay? So how can we create these numbers in a clever way such that each time we compute only a smaller number of numbers and then use the answers to create the subproblems to create the values for the full set. Okay, so that will be the key idea. And if you can make that work recursively, you will have a recursion of the form t of n will be 2 times t of n over 2. Remember what happened? We have to evaluate the polynomial of degree, remember odd and even, right? There are 2 polynomials you have to evaluate at the first half numbers, right? So we'll try to get a recurrence of the form t of n. We want to evaluate the polynomial at n different numbers. But what we will do instead is we'll evaluate the odd polynomial and even polynomial at only half the numbers, right? So how much work will we do? We'll do 2 times. Now the odd polynomial and even polynomial of degree n over 2, right? So it is 2 times t of n over 2 plus how much extra work will we do to put them together? We'll do n work, right? So that's the recurrence we will get, and that will lead to n log n. Okay? Does it make sense? That's the idea, right? High level, yeah. I mean, yeah.
How about the constants?
Sorry?
How about the constants?
How about?
If you have, like, let's say x squared plus 3.
Yeah.
How about 3? Like, you still have to evaluate that.
Plus 3?
Yeah, like this.
No, 3 is part of the odd degree polynomial, right? I mean, even degree polynomial. Okay, see, let's go back. So, if I have a polynomial of this form, this is a even and this is a odd, right? So this is part of the half degree polynomial we got. Maybe I didn't understand your question properly. Yeah, okay. Yeah, I mean, so is that okay? Yeah, okay. Okay, so all right. So now the question is, what does it mean to be able to do recursion, right? So let's do some magic, right? We'll assume some that we can do some magic, and then we'll figure out how to do the magic. Okay. So this is going to be a little bit abstract, right? We'll define. So given a set X, what is the square of that set X? It's take all the numbers and square them. Okay. Okay, that's it. The definition of square of x is simply the set of all numbers which are squares of the numbers in x. Remember, it's a set. So what happens? Why will the square of x be a? If I have, what's the advantage of a square, right? If you have 2 numbers which are negations of each other, they'll both become only one number, right? So maybe it'll, that's just the definition. Square of x is take all the numbers in x and square them, and you get a new set. Okay? Okay. We say that a set of numbers is collapsible if somehow magically the square of x is a subset of x. Okay? That is, all the squares are also in the set, and they're exactly half. The size of square of x is exactly half. Okay? Okay, give me an example of where that can happen. Small set of size 2. 1 minus 1, right? Yeah? If I start with 1 minus 1 as x, what happens if I take the squares? We end up with 1, right? Okay. Can you try to think of a set which is size 4? Sorry? Yeah?
1 minus 1 iota minus 1.
Sorry?
1 minus 1 and then iota minus 1. Are we allowed complex numbers?
So see, he's asking, are we allowed complex numbers? Suppose we allow complex numbers. Okay, then 1 minus 1, I minus I will work, right? Yeah? Does it make sense? Okay, why? Okay, 1 minus 1 will collapse. Right? Right? I square will become minus 1, right? Okay? Agreed? Okay. But it seems like, you need complex numbers, right? For 4 already. Okay, but let's forget about it, right? It's just a definition, right? We don't know where these numbers will come from, but let's assume that somehow we can create them, right? So, but what is collapsible means that it satisfies this property, right? If you start with x and take all the squares, we get half the size of half the original set. Basically, it belongs to is a subset of the original set and is exactly half. And we see that we could create 1 minus 1, and if we went to 1 minus 1 complex numbers, we could do it even with 4. Okay? But let's not worry about whether we can do it or not. It's just a definition. Okay. Now we'll say something even stronger. A set of numbers is called recursively collapsible if it keeps collapsing like that, right? Formally, that start with size n numbers, we take the squares, what do we get? We get a subset of size exactly half of the original set. Okay? And that's also recursively collapsible. That means that if you take the squares again, we'll get a subset of that which is half. And then if you do it again, we'll keep going like that all the way to n size set will go all the way to size 1. Okay, what is an example we saw? This is recursively collapsible of size 4, right? Right, if you square it, we'll get 1 minus 1 again. And 1 minus 1 is again, if you square it, we'll get 1. Nice square collapse, that's called a recursively collapsible set. Right? We don't know where they exist, right? Suppose we had somehow a magical set of recursively collapsible numbers. Okay? Then I claim that we can implement the divide and conquer strategy that we kind of vaguely alluded to. Okay? So how can we do that? Here is the idea, right? Here is the algorithm. My evaluation will be on this recursively collapsible set of numbers, right? I get to choose them, right? So that I want to evaluate my polynomial at all the numbers of this recursively collapsible set. How am I going to do it? Here is how I am going to do it, right? So I want to evaluate a polynomial A on this recursively collapsible set X with n numbers. If n equal to 1, degree is 1, I just return the polynomial, right? There's nothing to do. That's a base case. Okay? Otherwise, I first compute the square of the set X. What happens if I compute the square of the set X? Because it is collapsible, it becomes half, right? Okay. Now I'll recursively compute the odd polynomial, A odd on that set, because it's degree n over 2, remember? The odd degree polynomial has degree n over 2, right? I'll compute it on this n over 2 numbers, right? Because it's a degree n over 2 polynomial. I'll also compute the even degree polynomial, which is again degree n over 2, on the square of x, which is of size n over 2. Okay? Once I have, how many numbers will I get? N over 2 values I'll get, right? And then I can, using those values, I can compute the value of the polynomial A and all these original n numbers on set x. Why? Why is because A of x is A even of x plus x times A odd of x, right? A of x is A even of x square plus x times A odd of x square, right? But remember, x squares were there in the square, right? We computed all of them, yeah, right? Okay, let's go back. See, what is A of x? A of x is A even of x square plus x times A odd of x square, right? Remember, in the recursive problem, we get all these values, right? Because x square is in the square of, right? All the squares are in the set square of x, and we get these numbers and these numbers for all numbers in square of x, capital X, right? And then we can put them together, right, to get the value of the polynomial on all the collapsible set x, right? So what is the running time of this? Is t of n is 2 times t of n over 2 plus O of n, right? It's like a simple divide and conquer recurrence. That makes sense? Yeah? So if you had this magical recursively collapsible set, you can get a very fast algorithm. Okay? Does that make sense or no? Yeah? Okay. Questions? Yeah.
I don't really get why, in like A even and A odd, why it's squared? Why the x is squared?
Oh, because that's so okay. Let's go back to the example. Maybe that's see. I mean, so if I take a polynomial of this degree, right, of degree 5 here, and I split it into 2 polynomials, right? Okay. Now, what do I get? I get a polynomial with how many coefficients? Half the coefficients, right? I want to think of it as a polynomial of smaller degree. Okay? I don't want to think of this as a polynomial with degree 4. I want to think of this as a polynomial of degree 2. So, if I want to think of it as a polynomial of degree 2, I have to take out x square and think of x square as x. Right? So, that's why we write it as a of x is not a even of x, but a even of x square. Okay? So, this is a polynomial of, to get the right degree, I need to treat it as a smaller degree polynomial, but I square all the x's, right? So to evaluate a at a number x, we want to evaluate a even not at x, but at square of x. So what this recursion is doing is it's making a smaller half the degree polynomial, but the price you have to pay is that, I don't want the value of that polynomial at x, but at x square. So that's why I evaluate both a even and a odd, not at the original numbers, but on the squares of the original numbers. Okay? Right? So that's what we are doing, right? In the algorithm, we are not evaluating a odd and a even at the original numbers, but on the squares of the original numbers. Okay? Okay, but the squares also have to go down, right? Otherwise I will be evaluating the smaller degree polynomial on, if I have to evaluate them on many numbers, that's not helping me, right? So if I had the magical property that if I take the set x and square all the numbers, they suddenly become half, then somehow everything works very nicely. This all looks very magical, right? Because of this property of this squares. How can you have these collapsible sets? We can't have collapsible sets if you stick with real numbers. But we'll see that if you go to complex numbers, you suddenly get these magical numbers. Okay? All right. Okay, so there are two parts, there are many parts to this problem, right? It's a bit complicated thing, but I want you to appreciate the complexity of algorithm design by combining tools from many areas, right? See, this recursion is trivial. In a certain sense, it's not very hard. You have to just make sure you understand some details, right? It's a simple divide and conquer. It's really not very hard if you just stare at it for a little bit, right? It's a simple divide and conquer. The algorithm is not the hard part here. The magic is where do you get these numbers from? It requires some idea. First, we have to go from the coefficient representation to the sample representation. That itself requires some understanding some polynomial properties of polynomials, right? But then once we had that, the algorithm is simple, modulo creating these numbers. Okay? So you want to separate out your understanding of the divide and conquer methodology, which is very simple, from how do we construct these magical numbers. Okay? If you had these magical numbers, everything is simple, but how do you create these magical numbers, right? Again, math comes to the rescue, right? So,
how hard is it to come with a collapsible set for a given?
no, so we see here is what we want, right? We want how hard it is. Yeah, well, it's not. I mean, we'll see that it's not at all hard, except that they don't exist in real numbers. We have to go to complex numbers. And so I will skip, we'll do that on Friday, right? So, but before Friday, try to make sense of the basic divide and conquer, assuming that magical numbers exist, this collapsible set. That is not very hard. You just need to understand that a of x can be written as two smaller degree, half degree polynomials, but you're not in the variable x, but in the variable x square now. So that means that to evaluate a on this set, you need to evaluate these smaller degree polynomials and the squares. Okay, and the squares should be small too. Right? That's all there is in the algorithmic context, right? The rest is basically algebra. I mean, okay, all right? Okay.
So this quantity is posted after the
Yeah.
the two arrays used for y.